everyone, my name is Madhuri Gupta, Assistant Professor, Department of Computer Science and Engineering, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today's topic is Minmax Search. Before that, let's have a quick recap on last lecture on constant satisfaction problem. Optimality. In some cases, CSPs have an objective function associated with the term, and the goal is not only to find a solution but to find an optimal solution that minimizes or maximizes the objective function. Applications. CSPs have wide range of applications including scheduling problem, map coloring, Sudoku puzzles, and logistic planning, among others. So we have solution methods, backtracking. One common approach to solve CSP is backtracking, where the algorithm explores different assignments of values to variables and backtracks when the constants are violated. Constant propagation. This technique reduces the domain of variables based on the constants. Examples includes our consistency algorithms. Heuristics. Heuristic like minimum remaining values MRV and most constraining values MCV can be used to guide the search for solution efficiency. Forward checking. This technique keeps track of the remaining legal values for the unsigned variables, reducing the search space. In essence, CSPs are a powerful framework for modeling and solving problems that involves constants on variables. They provide a structured way to represent and solve a wide variety of real-world problems in fields such as scheduling, planning, and optimization. So now we will start with the today's topic, Minmax algorithm in artificial intelligence. Minmax algorithm is a recursive or backtracking algorithm which is used in decision making and game theory. It provides an optimal move for the player, assuming that opponent is also playing optimally. Minmax algorithm uses recursion to search through the game tree. Minmax algorithm is mostly used for game playing in AI, such as chess, checkers, tic-tac-toe, and so on, and various two-player games. This algorithm computes the min-max decision for the current state. In this algorithm, two players play the game. One is called max and other is called min. Both the players fight it as the opponent player gets the minimum benefits while they get the maximum benefit. Both players of the game are opponent of each other, where max will select the maximized value and min will select the minimum value. The min-max algorithm perform a depth-first search algorithm for the exploration of the complete game tree. The min-max algorithm proceeds all the way down to the terminal node of the tree, then backtrack the tree as recursion. So let's understand the game theory. In general game, the max-min value is the highest values that the player can be sure to get without knowing the action of the other players. Equivalently, it is the lowest value the other player can force the player to receive when they know the player actions. Its formal condition is as follows. I is the index of player of interest, denotes all other player except player I, is the action taken by player I, denotes the action taken by all other players, is the value function of player I. Calculating the max mean value of a player is done in a worst case approach for each possible action of the player. Here we have pseudocode for min-max algorithm. First, function min-max, node, depth, maximizing P layer is second, if depth is equal to 0 or node is a terminal node, then step 3, return static evaluation of node. Step 5, if maximizer player, then for maximum player R. Step 6, max evaluation is equal to infinite. 7, for each child of node do evaluation is equal to min-max child depth minus 1, false. Step 9, max evaluation is equal to max evaluation dot evaluation, that means gives max return of the values. Step 10, return max evaluation value. Step 11, else, for minimizer player, min evaluation is equal to plus infinity. For each child of node do evaluation is equal to min max child depth minus 1, true. Min evaluation is equal to min evaluation, that means gives the min return value. Step 17, return min evaluation. So first is initial call, min max node 3, true, working of min-max algorithm. The working of the min-max algorithm can be easily described using an example. Below we have taken an example of game tree which is representing the two-player game. In this example, there are two players, one is called maximizer and other is called minimizer. Maximizer will try to get the maximum possible score and minimizer will try to get the minimum possible score. This algorithm applies DFS, that means depth first search. So in the game tree, we have to go all the way through the leaves to reach the terminal nodes. At the terminal nodes, the terminal values are given, so we will compare those values and backtrack the tree until the initial step occurs. Following are the main steps involved in solving the two-player game tree. Step 1. In the first step, the algorithm guarantees the entire game tree and apply the utility function to get the utility values for the terminal states. In the below tree diagram, let's take A is the initial node of the tree. Suppose maximizer takes the first term which has worst case initial value minus infinity and minimizer will take the next term which has the worst case initial value plus infinity. So here in the tree we have A as a maximizer, then we have successor B and C as minimizer, then we have the successor of B as D and E, and we have successor of C as F and G which has the maximizer label, and again we have successor of D which has H and I, then we have successors of E, J and K, and we have successor of F which has L and M, and we have successor of G as N and O. In the terminal we have value minus 1, 4, 2, 6, minus 3, minus 5, 0 and 7. Step 2. Now first we find the utilities values for the maximizer. Its initial state or initial value is minus infinity. So we will compare each value in terminal state with the initial value of maximizer and determine the higher node's value. It will find the maximum value along the all. For node D, max minus 1 and minus infinity, that is equal to max minus 1, 4 is equal to 4. For node E, max is 2 is compared with minus infinity, so we have 2 then 6, so we get the final value 6. For node F, max 3, -3 and minus infinity. So max is equal to -3 minus 5. So we get the value -3. For node G, max 0, comma minus infinity. So max is 0, comma 7. So we get 7. So in this diagram, we have the next step where we got the changes value in our max level. So you can see the value is upward as D is equal to 4, E is equal to 6 and F is equal to -3 and G is equal to 7. So we have solved the terminal to the upward level. Step 3. In the next step, it's turn for minimizer. So it will compare all nodes value with positive infinitive and will find the third layer node values. For node B, min 4, 6, that means 4. For node C, min is compared to -3 and 7, so we will get the minimum value -3. So you can see this value is updated in the diagram. So we have B is equal to 4 and C is equal to -3. Step 4. Now it's turn for maximizer and it will again choose the maximum value of node's value and find the maximum value for the root node. In this game tree, there are only 4 layers. Hence, we reach immediately to the root node. But in real games, there will be more than 4 layers. For node A, max is equal to 4, comma -3. So we have to choose the maximum value. So we will get 4. So you can see in the diagram, we finally get the value of A is equal to 4. That was the complete workflow of Minmax 2-player game. So now we will look for the another example. Suppose the game being played only has the maximum of 2 possible moves per player each turn. The algorithm generates the tree on the right where the circle represents the moves of the player running the algorithm maximizing player and the square representing the moves of the opponent minimizing player. Because of the limitation of computation resources as explained above, the tree is limited to look ahead of 4 moves. The algorithm evaluates each leaf node using a heuristic evaluation function, obtaining the values shown. The moves where the maximizing player wins are assigned with the positive infinity, while the moves that lead to a win of minimizing player are assigned with negative infinity. At layer 3, the algorithm will choose for each node the smallest of the child node values and assign it to that same node, that is, the node on the left will choose the minimum between 10 and the positive infinity, therefore assigning the value 10 to itself. The next step in level 2 consists of choosing for the node the largest of the child node values. Once again, the value of assigned to each parent node, the algorithm continues evaluating the maximum and the minimum values of the child nodes alternatively until it reaches the root node, where it chooses the moves with the largest value represented in the figure with the below arrow. This is the move that the player should make the order to minimize the maximum possible loss. So you can see the diagram where you have different representation. So you can see the value where we have 4 layers starting from the 0 layer which has the max player. We have the value 7, and in the child node we have value 10 and -7. Then we have explored it till the terminals and we have compared all the terminals with 10 with infinity 5 with -10, 7 with 5 and -8, and then -7 and -5. So in the upper level we get the value 10, 5, 10, 5, minus infinitive and minus 7. And the upper layer is max layer, so we get the max value 10 and 10, then 5 and 7. Then in the upper level we have 10 and minus 7, so it is a final value minus 10 and minus 7, so we'll get the minus 7. You can see in this animation it is start from the root, then it explore in a depth first search way, so the next successor of that root node, then the next successor, then all the visited node is represented with blue and the exploration is represented by green, then finally the terminal is represented by pink. So we have the value 5 and 6 and it is a minimizer, so we pass the value as minimum value 5. Next it will compare with the next level, so we again pass the value 5 and we explore in the green, then we got the value in the terminals 7, then again 7 is compared, then we got the another value 4, then again it is compared 7 and 4, then again we got the value 5. So all the three values compared and finally we will get the 4. Then again we have to compare 4 and 5 and again 5 values passed into upper level, then the again blue circle represent the remaining other value, so it will change to 3 because 3 is another minimum value. Then we explore the next part of our tree, it is representing in the green and all the visited node is represented by blue, and finally we have got the terminal value is 6. So again this 6 is passes to the another level, and then we got the another terminal value as 5, and again we have to compare this value to the max layer, then again we got the value 9, then it is also again compared, then we finally get the value 6, and then again we have to traverse in the next part of the tree, then the 6 is passes, and then finally we come to the terminal and we will get the value 7, then 7 is compared and the 7 value is passed, then again values compared, we will finally get the value 6. So the root node will get the value 6, then again it explored till the terminal and we get the 5 value, then again 5 is compared, then we will get the 5 value, then again it explored till terminal, we get the value next value 9, then 9 is compared and finally we get the 5 value, then again the value of terminal is 8, then 8 is compared and we finally get 8, then again the 6 is the terminal value, then again 6 is compared and we have visited all the node. So finally this green line is showing the path where we will get the optimum value. So we have another example finding optimal move in tic-tac-toe using min-max algorithm in game theory. Let us consider what we have learned so far about min-max and evaluation function to write a proper tic-tac-toe AI, artificial intelligence, that plays a perfect game. This AI will consider all possible scenarios and make the most optimal moves, finding the best move. We shall be introducing a new function called find best move. This function evaluates all the available moves using min-max function and then return the best moves the maximizer can make. The pseudocode is as follows. Function find best move board. Best move is equal to null for each move in board. If current move is better than best move is equal to current move. Return best move. Min-max to check whether or not the current value is better than the best value, we take the help of min-max function, which will consider all the possible way the game can go and return the best value for the move, assuming the opponent also play optimally. The code for the maximizer and minimizer in the min-max function is similar to find best move function. The only difference is instead of returning a move, it will return a value, hence is the pseudocode. Function min-max board depth is min-max player. If current board state is the terminal state, return value of the board. If is maximizer player, best value is equal to minus infinity. For each move in board, value is equal to min-max board depth plus 1 false. Best value is equal to max best value value. Return best value. Else best value is equal to positive infinity. For each move in board, value minimize board depth plus 1 true. Best value is equal to minimum best value value. Then return the best value. Checking for game over state. To check whether the game is over and make sure that there are no moves in left, we use isMoveLeft function. It is a simple, straightforward function which checks whether a move is available or not and return true or false respectively. Pseudocode is as follows. Function is move left board. For each cell in board, if current cell is empty, return true. Return false, making our AI smarter. One final step is to make our AI a little bit smarter, even though the following AI step, preferably it might choose to make a move which will result in a slower victory or a faster loss. Let's take an example and explain it. Assume that there are two possible ways for X to win the game from a given board state. Move A, X can win in 2 moves. Move B, X can win in 4 moves. Our evaluation function will return a value of plus 10 for both A and B, even though the move A is better because it ensures a faster victory. Our AI may choose B sometimes. To overcome this problem, we subtract the depth value from the evaluated score. This means that in case of victory, it will choose a victory which makes least number of moves, and in case of a loss, will try to prolong the game and play as many moves as possible. So, the new evaluation value will be move A will have a value of plus 10 minus 2 is equal to 8. Move B will have the value of plus 10 minus 4 is equal to 6. Now, since move A has a higher score compared to move B, our AI will choose move A over move B. The same thing must be applied to the minimizer. Instead of subtracting the depth, we add the depth value, as the maximizer always tries to get as negative a value as possible. We can subtract the depth either inside the evaluation function or outside it. Anywhere is fine. I have chosen to do it outside the function. Pseudocode implementation is as follows. If maximizer has 1, return win score is equal to minus depth. Else if minimize has 1, return loss score plus depth. In this tree, you can see we have the structure cross 0 cross 0 0 cross, then cross, then we have blank, 2 blank. So this 2 blank, then again we have to explore it. So we will get cross 0 cross 0 0 cross cross 0, and the another is cross 0 cross cross, 0 cross, 0 cross cross, then cross, then we have blank and 0. So in this way we have solved this, so it will take the 10 value minus 10 value, then again we have explore it, so we will get x cross 0 cross, cross 0 cross, 0 cross cross, then cross cross 0. So we have win condition, so we will get the value plus 0. Then and the next explore, we can next explore the tree. So we have cross 0 cross, 0 0 cross, then blank cross blank. So we have two options. So we have cross 0 cross, 0 0 cross, then 0 cross. Then we have another option, that is cross 0 cross, 0 cross cross, and 0 cross cross. So we have plus 10 value. And the another way is we have cross 0 cross, 0 0 cross, then cross 0. So we have explored it. So cross 0 cross, 0 0 cross, then cross cross 0. So we have plus 0 value, and the remaining exploration is cross 0 cross, 0 0 cross. So we have blank blank cross, so we have the value plus 10. Then finally we have to come to the another level where we have the final value 0 plus 10 and 0. So this image depicts all the possible paths that the game can take from the root board state. It is often called the game tree. The three possible scenarios in the above example are: left move. If x play 2 0, then 0 will play 2 1 and win the game. The value of this move is minus 10. Middle move. If x plays 2 1, then 0 will play 2 2, which draw the game. The value of this move is 0. The right move. If x plays 2 2, then he will win the game. The value of this move is plus 10. Remember, even though x has a possibility of winning if he plays the middle move, 0 will never let that happen and will choose to draw instant. Therefore, the best choice for x is to play 2 2, which will guaranteed a victory for him. We do encourage our readers or our learner to try giving various inputs and understanding why the AI choose to play that move. Minmax may confuse programmers as it thinks several moves in advance and is very hard to debug at times. Remember, all the implementation of Minmax algorithm can be applied any two-player board game with some minor changes to the board structure and how we iterate through the moves. Also, sometimes it is impossible for Minmax to compute every possible game state for complex games like chess. Hence, we only compute up to certain depth and use the evolution function to calculate the value of the board. So, properties of Minmax algorithm. First is complete. Minmax algorithm is complete. It will definitely find a solution if exists in the finite search tree. Optimal. Minmax algorithm is optimal if both opponents are playing optimally. Time complexity. As it performed DFS for the game tree, so the time complexity of Minmax algorithm is order of b to the power m, where b is branching factor of the game tree and m is the maximum depth of the tree. Space complexity. Space complexity of Minmax algorithm is also similar to DFS, which is order of bm. Limitation of Minmax algorithm. The main drawback of Minmax algorithm that is gets really slow for complex games such as chess, Go, etc. This type of game has a huge branches factor and the player has lots of choices to decide. This limitation of the min-max algorithm can be improved from alpha-beta pruning, which we will discuss in our next topic. So, our upcoming lecture is about alpha-beta pruning. Alpha-beta pruning is a powerful optimization technique used in game trees and search algorithms, primarily in the context of two-player adversarial games like chess, checkers, or tic-tac-toe. It helps reduces the number of nodes evaluated during the search process, significantly improving the efficiency of finding the best move. Thank you for watching, and we will see you in the next chapter.